In this last video, what I want to do is give you some examples of problems that you can understand given the stuff that we've already introduced that I find very interesting and come up in my research life. So this is a little selection of some of Nathan's favorite problems. So what we're going to do is let e be a fixed positive integer. And then we're going to define a function f sub e of p. So p is going to be a prime number, and e is going to be fixed. So we'll let FEP be the number of isomorphism classes of groups of order p to the e. So p to the e is some finite number. E is fixed, p is varying, and we want to know how the number of isomorphism classes of groups of order p to the e is varying. So remember, isomorphism classes, we now know what it means for two groups to be isomorphic. It's not hard to see that there's only finitely many different possible groups of order like 100. So we can just divide them up into like, out of all of those possible group structures, which ones are isomorphic to each other, which ones are not isomorphic to each other. Okay, so what do we want to understand? E is fixed, p is varying. What kind of function is this? All right, so what do I mean? So f1 of p equals 1. What is that reflecting? Well, we're going to prove this soon, that every group of order p, where p is prime, is isomorphic to z mod pz, the group of integers modulo p under addition. So we're going to prove lots of classification type results like this. All right, so let's move on. What about f2 of p? Well, this is 2. What is this saying? Every group of order p squared is isomorphic to one of two possible groups. You could have z mod p squared z, the group of integers modulo p squared, or z mod pz cross z mod pz. So what is this? This is the direct product of two groups. So the underlying set is the Cartesian product and what is the operation here? Well, if you take a pair A comma B, where now A is in your first thing, B is in your second thing, and you do the operation to C comma D, this is just A dot C comma B dot D. So the operation is done component-wise. So in this example, our two groups are the same. They're both z mod pz. But you could imagine, in this case, the operation is the operation in the first group. And in the second coordinate, the operation is the operation in the second group. It will not be hard to see that these two groups are not isomorphic to each other. They give you two different groups of order p squared. But we'll prove that every group of order p squared is isomorphic to one or the other. Okay. Let me give another example. What about f3? f3 of p is 5. So I'll just say there are 3 abelian groups, non-isomorphic abelian groups, and there are 2 non-abelian ones. And we'll prove this later. I mean, the most concrete example to keep in mind is if p is 2. What I'm saying is there are 5 groups of order 8. There are 3 abelian ones. And then there are these 2 groups. One we've already seen, D8, is a non-abelian group of order 8. I guess I haven't shown you that it's non-abelian, but you can check that rotating and then reflecting is not the same as reflecting and then rotating. And there's one more called the quaternion group, Q8, and that'll be another group that comes up quite a bit. So I'm going to pause and erase, then I'm going to tell you what is known about this problem as you change this number 3 to like 4 or 5 and so on. So what else is known about this function? F4 of P is equal to 15. There are 15 isomorphism classes of groups of order P to the 4th, except when P is 2. The number of isomorphism classes of groups of order 16 is only 14. Somehow, 16 is too small to be capturing that 15th different thing that can happen. So there is a formula that is a number, except there's one special case at P equals 2. What happens for groups of order P to the 5th? Here's the formula. F5 of P is 2P plus 61 plus 2 times the greatest common divisor of P minus 1 and 3 plus the greatest common divisor of P minus 1 and 4. So what is this saying? When P is 1 mod 3, you're picking up an extra pair, and when P is 1 mod 4, you're picking up an extra group. That formula holds if P is at least 5. But 2 to the 5th is too small to capture all these things. There's only 51 groups up to isomorphism of order 32. And, this should be a 5. And there's only 67 groups of order 3 to the 5th up to isomorphism. So what kind of function is this? It's a quasi-polynomial function. This is sometimes called PORC, P-O-R-C. It's a polynomial on residue classes. Meaning, well, there's a special case when P is 1 mod 3. There's a special case when P is 1 mod 4. How do you tell if something's 1 mod 3 and or 1 mod 4? You can look at P mod 12. So for each residue class mod 12, there is a polynomial formula for F5 of P. But you might say, well, there's these two special cases for P equals 2 and P equals 3. But that's captured here. Because for all primes that are 2 mod 12, the formula is the number 51. Because there's only one prime that's 2 mod 12. Any number that's 2 mod 12 is even. So this quasi-polynomial language captures these small number special cases. Okay, so what's supposed to be true in general? There's this conjecture of Higman that's several decades old, which says for any fixed E, Fe of P is PORC, quasi-polynomial, that this type of behavior should continue to happen. So what does that really mean? Given E, there's some integer, me, some period, so that for every I between 0 and me minus 1, for every possible residue class mod me, there exists a polynomial, qi, so that the formula for FEP is qi evaluated at P for all primes that are I mod this me. So for each residue class, there is some polynomial formula. It doesn't say anything at all about how big that period is in terms of E, or like how these different polynomial formulas relate to each other. All that the conjecture says is that these quasi-polynomial formulas exist. This is known to be true for, well, here's an example for n equals E equals 5. This should say E. True for E less than or equal to 7. So it's also true for E equals 6 and 7. And what's currently the state of the art is this is probably false once E is at least 10. So here's the idea. You can write this number of isomorphism classes of groups of order P to the 10th as a sum over a whole bunch of big complicated terms. And we know that one of those terms is not quasi-polynomial. How do we know that? Well, it involves the number of points on a certain elliptic curve modulo P. And that number of points is known to vary in a non-quasi-polynomial way. So it's really kind of neat that this ends up involving some number theory rather than just pure straight-up group theory. So I could talk about this problem for a long time. I have a good reference in mind. I'm going to stop and tell you about another kind of problem that you can understand given what we've talked about so far. The next question I want to talk about is about counting the number of subgroups contained in some fixed group. So here's an example. How many subgroups of Z cross Z, remember this is this Cartesian product thing, the underlying set is z cross z, and the addition is component-wise, that you just have a comma b plus c comma d is a plus c comma b plus d, just like how you add vectors. So how many subgroups of z cross z have index at most x? Let's call this n sub z2 of x. We want to know, how does this grow as a function of x? So rather than tell you the answer, let me just say, same question for z. How many subgroups of z have index at most x? Well, what we're going to see very soon, probably next week, is that every subgroup of z is of the form n times z, all the multiples of n inside of z for some positive integer n greater than or equal to 1. And it's not hard to show that the index of this subgroup, nz, inside of z is, well, it's exactly the size of z mod nz, which is n. So what is this saying? For each positive integer n, there is one subgroup. So how many subgroups have index at most x? Well, it should be like x, or the floor of x if x is not an integer. So this question's pretty easy to answer. So let me just tell you what happens for z2. So here's the fact. So n z2 x is asymptotic to pi squared over 12 times x squared. Okay, so what does this mean exactly? So if this asymptotic notation is maybe not familiar or it's been a little while, this just means that the limit as x goes to infinity of the ratio n z2 x over whatever this is, pi squared over 12 times x squared, this ratio goes to 1. So I love this. I feel like this is crazy because z, it's just integers, right? And all you're doing is you're taking like the integer grid in the plane. You're taking like the integer lattice and you're asking for, you know, some counting problem about the number of special substructures that it has. And you end up with this pi squared over 12, which feels like it totally came out of nowhere. So let me tell you what the idea is. This is something that I think about a lot in my research life, is there's this thing attached to an infinite group called a zeta function. So calculate the zeta function for the group z cross z, or more standard to write it as z squared. So if you've thought about zeta functions before, it's probably because you've heard of the Riemann zeta function, right? Which is zeta of s is a sum from n equals 1 to infinity of 1 over n to the s. And the Riemann zeta function is exactly what you get when you calculate the zeta function for the group G. So what you get for Z2 is you get a product of two slightly shifted copies of the Riemann zeta function. And then there's some cool like analytic properties of this complex, this function of a complex variable gives you this group theory fact as a consequence. So you can change this in all different kinds of ways. You can say, okay, maybe I don't just want to count subgroups, but I want to count subrings. And I don't just want to do this for Z2, but I want to do it for Z to the n. Or one thing I mentioned was that there's sort of another thing you can do with rings is not just count their subrings, but count these objects called ideals. And if you try to do a similar counting problem here where you count ideals of bounded norm inside special kind of rings, it leads you to a lot of what is a big focus in the math 232 in the number theory sequence. So again, I could talk about this forever, and I would like to in office hours, but I'll stop here and I'll switch to one other sort of very different feeling problem, and that'll be the end of the first set of lecture videos. The last example problem I want to introduce is much more combinatorial. So I'm going to start by saying some very basic things about graphs. So a graph, G, is just a collection of vertices and edges. You have some finite number of vertices, and what is an edge? It's just a pair of vertices. It connects two vertices. So an edge is like E connects VI to VJ. So given a graph, you can encode its structure in a matrix called the adjacency matrix. So what is the adjacency matrix of a graph? It's a size of V times size of V matrix. So you have one row and column for each vertex, and the entries are just 0 and 1. And you put a 1 in position I, comma j if there's an edge from vertex I to vertex j. Otherwise, you put a 0. So this is a symmetric matrix that has zeros all along the diagonal. So here's an example. Just take a square, a cycle of size 4. The adjacency matrix looks like this. 1 is connected to 2 and 4, but not 3. So in the first row, you have 0, 1, 0, 1. Same thing for the first column. You can fill in the rest. Let's define a diagonal matrix called D, where the diagonal entry in the ith row is just going to be the number of edges connected to I. So in this case, the vertex 1 has 2 edges. The vertex 2 has 2 edges. Every vertex has 2 edges. This matrix D minus A is called the combinatorial Laplacian. For people who have thought about like analysis and differential operators, the Laplacian plays a really big role. This is a kind of discrete combinatorial version for graphs. There's a good reason it's called this. In this example, here's D minus A. 2's on the diagonal, minus 1's in the spots where the adjacency matrix had 1's. So what is true about this matrix? For one thing, it's singular, because every row and column sum to 0. Right? There's 2 here, there's a minus 1, a minus 1. Right? If there's 2 edges connected to V, to vertex I, that means in the ith column of the adjacency matrix, there will be that number of 1's. So when you subtract, every row and every column is going to add up to 0. So that means 1, 1, 1, 1, 1, or is in the kernel of this matrix. Okay, so a matrix is a linear map. D minus A gives a linear transformation from Z to the number of vertices to Z to the number of vertices. So what does this map tell us about this graph? There's this whole field of spectral graph theory is one field where you try to understand graphs by taking things like the adjacency matrix, the combinatorial Laplacian, and looking at like eigenvalues and eigenvectors. So I want to zoom in just on this map, and I'm going to pause and erase, and then I'll tell you the sort of group theory problem that is the last example that I want to talk about here. We started with a graph, and we got this matrix, the combinatorial Laplacian, D minus A from it. We said that a matrix is the same thing as a linear map. So we get this map from Z to the number of vertices to Z to the number of vertices. The co-kernel of a map is the same as a co-kernel of a matrix. It's the codomain modulo the image of the map. So we'll talk much more about quotient groups soon, but maybe you can imagine what this is. And what is this image? It's just the column span with coefficients in Z of this matrix. So because this matrix is singular, that 1, 1, 1, 1, 1 is in the kernel, any integer multiple of that vector is also in the kernel. So we get a copy of Z in the co-kernel. And then we get something else. We get this SG. And it's a fact that SG is a finite abelian group if and only if the graph G is connected. A tree is a special kind of graph. It's a connected graph with no cycles, which just means you can't start at a vertex, walk around on edges you haven't been to before, and wind up back where you started. So nothing like this. The matrix tree theorem is a big theorem in this area. It says that this matrix tells you something structural about the graph. That the order of this group, SG, is the number of spanning trees of the graph. So what's a spanning tree? It's a tree that has the same vertex set as the graph you started with. So you delete some edges of your graph. Maybe your graph has lots of cycles. And you delete some edges, and you get a tree. That's what a spanning tree is. So this group comes out of this matrix, and the size of this group is meaningful. Okay, well, you have a machine now where you start with a graph, you get a matrix, and it gives you a group. And you know the size of this group means something. Well, what else can we do with finite abelian groups? We can kind of break them up into their prime factor pieces. So this is something we'll talk about much, much more. Let P be a prime. We're going to prove something called Celo's theorem. It's more interesting for non-abelian groups, but the P-Celo subgroup of an abelian group, finite abelian group, whatever, is unique. And what is it? It's the subset of all the elements of the group that have P power order. So any element whose order is a power of P goes in that subgroup. We'll talk much more about the order of elements of a group coming up soon, but I would imagine some of you already know what that means. So the question is, now we start with a graph, we get a matrix, we get a group, you can take its P-Celo subgroup. So if you just pick a graph at random, what kind of groups are you getting here? So I'm going to pause and erase, and then I'll give you a really concrete instance of this question that I find very surprising and interesting. This group, SG, gets a special name. It's called the sandpile group of the graph G. There's a good reason for that. These groups come up in a lot of different places. And one of them is this model from physics about dropping grains of sand onto a vertex of a graph. And if you have too much sand on one vertex, it topples and spills over to its neighbors. And there's all these different ways to interpret this. I'll leave that for now. The question I want to ask is, how are these P-Celo subgroups of sandpile groups of random graphs distributed? Okay, who cares? Well, one thing to note is the order of this group is the number of spanning trees of the graph. So what does it mean for the number of spanning trees to be odd? That exactly means that the 2-Celo subgroup of this group is trivial, that there's no elements of even order. Okay, what does it mean to take a random graph? So what's a random graph on n vertices? One way of choosing a random graph is you have n vertices. There's n choose 2 possible pairs of vertices. So there's n choose 2 possible edges. I'm just going to flip a coin for each one and independently include it with probability 1/2. There's 2 to the n choose 2 power possible graphs I could get. Each one is equally likely. Okay, so for a fixed n, let's just take all these graphs and count how often is the 2-Celo subgroup trivial versus being non-trivial. And there is this very cool, relatively recent theorem of Melanie-matched Wood that says, as n goes to infinity, the probability that the number of spanning trees of a random graph chosen in this way is odd. Or equivalently, the probability that this group SG has no elements of even order, of 2-power order at all, is equal to a product where I is greater than or equal to 0 of 1 minus 2 to the negative 2i minus 1 power. So it's a product over all odd numbers I of 1 minus 2 to the minus odd. Okay, so what does that actually mean, though? This is 0.4194 something, something, something. So what I love about this is most of these what's the chance of this happening as n goes to infinity type questions, there's either a good reason why it happens with probability 1 or with probability 0, or with the, like, I don't know, even, odd, like maybe it's random, probability 1/2 exactly. And this is a cool example of something where you're really getting a probability that has this cool product formula that means something, and it's not so clear why until you really get into what's going on behind the scenes here. So it's a place where graph theory, linear algebra, group theory, all kind of come together. And I'm primarily a number theorist. I'm very interested in this type of results because of analogies with the way that random groups show up in number theoretic contexts. All right, so I'm going to stop here. I feel like that's enough about problems that I like. I'm happy to talk more about any of this. Of course, this is all just motivation. I wouldn't ask you to answer questions on an exam or anything about this kind of thing, but I hope that you find it interesting and motivating.